So if you look into the problem itself, right, the cantilever, okay, if you have a beam shown here, okay, a white flange, W18 times 35. So the properties are, if you can go and find from the internet itself, it will basically tell us that it's an I-beams, okay. Probably I will just draw it out. So right, so this is W18 times 35. We have the area A is 10.3. Then we have the so-called D is equal to 17.7, all in inch. Right, 10.3, 17.7. So the D here is this is the D. Then we have our BF flash is BF is 6. Then we have our so-called here is our TF. All right, so we have the TW and TF. Wait, hold on. So I have my also I, okay, along the second moment inertia along this x-axis is Ix is 510 inch or 4. Then I have my Iy. If you have along this axis y, it will be 15.3 weaker, okay, inch power of 4. The correct dimensions, hold on, let me show you the correct one. If you can search W18 times 35, so you can. So this will be our TF. Okay, so this will be our so-called TF. This will be our TW. Okay, so it is equals to, you need all this information later on to model 0.425. TW is 0.3 or in inch. Right, so you need all these informations to get it, or I can later on share with you. Let's say I find from here, I think 18 times 35. Okay, so I will share in the groups, the chats, so you can later on. This is the reference that I'm using. Okay, so it is subject to a uniformly distributed load of 1,000 pound per feet. Then this beam with 10 feet beams. Okay, you have a modulus of elasticity, or Young modulus is 29 times 10 power 6 pound per inch square. Okay, then determine the deflection of the beam. Okay, so we want to determine the deflections of the beam, okay, at B and C, right, and also the slope, okay, at or theta at so-called C itself. Okay, so if we treat it as a one what we call element itself, okay, one element itself, then we have this A, which is our I1, UI2, UJ1, UJ2. Then we have a 4 times 4 matrix. Our K elements here is a 4 times 4 matrix. All right. So what we do is we find the K itself. Okay. If you still remember, I mean, this K is basically our element is our global. In this case, just one element. So 4 times 4 matrix. Our load itself, because it's distributed, then we have like what I mentioned to you, negative. Okay, this is referring to UI1, UI2, UJ1, UJ2. Okay, then arrange everything. Then we have a full KU equals to F. Okay, then we can solve it. Before we solve it, we have to apply the boundary lah. So in this case, because it's a fixed free ends, right? Cantilevers, okay, fixed at the point node I, then probably our first two row, okay, in this case can be ignored lah, right? So in this case, this will be ignored. So we are focusing on a 2 times 2 matrix. All right. All right, so here we've solved this 2 times 2 matrix, then we can find our U21 and U22. So what it means here, our U21, which is negative 0.146-ish going down. U22 is the slope or rotations, which is a negative 0.00163 radian. So in this case, we can determine the deflection and the slope at endpoint C. All right. So if we want to determine the deflection at point B, okay, deflection at point B, then probably we have to make use of our shape functions. Okay, if you still remember our shape functions, okay, because it's not in the notes unless we use 2 elements. Here we use 1 element, then probably we need another so-called notes, or we use shape functions. Okay, so we have the shape, we have the v in our vx in the shape functions of s11, s12, s21, s22, right? So here, if we can substitute our x equal to L over 2 half or midpoint, then we can first find our shape functions. Here, if we do not need S11 and S12 because it is U11, U12 is 0. So here we only focus on the S21, S22. So S21, S22, if we substitute X equal to L over 2 into it, so we have our shape functions of S21 is 1 over 2, then S22 is negative L over 2. Then we substitute, basically find our VB or V at x equal to L over 2, then we have this S21, okay, which is U21, right, plus S so-called 22 U22 in this case, right? U21 and U22 already determines which is this one and this one. S21 and S22 at x equal to L over 2, which is this, at x equal to L over 2, which is this, right? So we can determine in this case our VB, our deflection at midpoint is negative 0.048. Okay, of course it's slightly lesser than the endpoint, which is lesser than the endpoint, which is negative 0.146. All right, so if you look against the second problems, we have another wide flange W310 times 52. We have a cross-sectional area 6650 mm square, depth of 317. The second moment of area is 118.6 times 10 power of 6. This is not 106, 10 power of 6. And the beam is uniformly distributed loads of 25,000 Newton per meter. We have the modulus of elasticity is 200. We are asked to find the vertical displacement at node 3, okay, this point, and the rotation at node 2 and node 3, right? And also compute the reaction force and the moments, okay, at node 1 and node 2 in this case. So what we can do here is we try to use 2 elements. So we have 2 elements here, 3 nodes, Okay, but we each node we have two degree of freedoms. So total we have 6 degree of freedoms. All right. Then here we have look into it. We have the stiffness matrix that is for one element. So now we have 2 elements. So basically we have a total of 6. Later on we have 6 degree. So we have a U11. I mean, this is more towards the first nodes and second nodes. Then we can substitute the length. Here is 5 meters. Okay, the second element is 2.5 meters. The load are the same. Then we have our K equals to EI over L cubes. So substitute everything in, right? With the length, with the E, with the I itself, then that gives us the first elemental stiffness matrix for the first elements. The second element is shorter, 2.5. So we substitute again 2.5. Then we also get the elemental stiffness matrix for element number 2. Right? Then we can probably assemble them, okay, into a 6 times 6 matrix. So here, this is our so-called, the first 4 is our so-called element number 1. So here is our element number 2. So basically, this is where we add up the 2 parts. So these parts add up with the element 1, these parts, right? So summation of these 2 will give these values. So that is our global stiffness matrix of 6 times 6, 6 degree of freedoms, right? Each node we have 2 degree of freedoms. Then that is our KG global stiffness matrix. Then we also have to find the load matrix in this case. Okay, load matrix also is a 6 times 1 matrix. So first we have the so-called the first elements. We have 2 nodes, 4 degree of freedom. So we have a 4 times 1 matrix. So again, we have negative WL square over 12, negative WL over 2. Then we have positive WL square over 12, right? Then our in this case, our length is 5 for the first element. For second element, we have 2.5. Okay, we have 2.5. But then here, these particular parts to get full assemble the load matrix, full assembly of load matrix will be this one. Okay. Then we want to determine a full one will be F equals to longer F 1 F 1 2 F 2 1 F 2 2 F 3 1 F 3 2. Right? So I J. So here, this will be our, let me use different color. This will be our F 1 1 F 1 2, right? So this is our F21 F22. This is also F21 F22 F31 F32. So these parts, okay, have to add with these parts. These parts have to be adding with these parts. All right. So end up you have a global load matrix, right? 6 times 1 matrix. Then we can put them into a global equations. F K U equals to F. Okay, 6 times 6, 6 times 1, 6 times 1. So we apply the what we call boundary. I mean, if you refer back to the questions, sorry. Right, so here is fixed, here is just a joint, a pin here, a ball here. So basically, we have our U 1 U 1 2 is equal to 0. Then here we also have a U 2 1 equal to 0. So U 2 2 is a non-zero. Okay, the rotation that it allow it to still have some sort of rotations. Then we have U 2 3 1 and U 3 2 in this case. So we have the three parts. So the first three row and column can be once you have applied the boundary, so probably 6 times 6 matrix here will be reduced to 3 times 3 matrix. Okay, to find U22, U31, and U32. So solving it, okay, send to the solver, okay, and in methods that you have familiar with, then we find our U22, U31, U32. Right. Then if you want to find our reaction force and moments, in this case, again, like what we have tried in the truss systems, this is what we have. R equals to KU minus F. Then put in all the 6 times 6 matrix, 6 times 1 matrix, 6 times 1 matrix that give us the reactions and the reaction force and the moments in this case. Okay, so that gives us this. All right. So that is about beams. Okay, in this case, if you we recap back, first we do finite element formulations of these beams. Okay, then from there we make use of the shape functions. Okay, from there one element we have 2 not 4 degree of freedoms. Then we have basically built the Stifler matrix, elemental Stifler matrix of 4 times 4. Then load matrix is 4 times 1. Then from there we can solve to find our displacement, or what we call the deflections due to transverse loading in this case. All right. So for the past 2 hours, we are looking into how to formulate it, how to build our Stifler matrix, and how to build our load matrix. Then from there, we can solve it manually. So we revisit these particular problems, see how we can solve it using ANSYS workbench. Okay, so that is just recap back on what we have manually calculated. We have discussed just now. You can see my screen, right? So if you look into this, that is how we calculate that. We get our U21 is negative 0.146, negative 0.00163, right? And our notes itself. So we revisit using ANSYS workbench, the same procedures. So you have a structure still. Okay, we can edit our Young modulus because PSI equals to 29 E6. Then we can draw it using a design modeler. In this case, probably you have to draw a length of 10 feet times 12, 120 inch. Okay, then with its cross sections, here we are looking into sorry, user defined cross sections, or else you can use the I sections, but then you have to edit re-edit the dimension, same with what we have I have provided to you just now, right? Or you find from the internet itself the link that I have shared with you. Okay, so we draw the what we call the dimensions accordingly, using the dimensions measured with the dimensions. I mean, in this case, you do not. I didn't use the grid, so I draw it manually. Then with the dimension set, then to make sure I have the correct dimensions, and also so-called here is the 6-inch, 0.3, 17.7, 0.4. If you can see from here, right, 0.425. These are all according to the internet, from the internet, the link that I've shared with you, the dimension of this particular W18 times 35, right? Then we create this line body itself, just 2 nodes itself, right? Then probably we can, yeah, if you look into it, here is actually, I think before this, it is still under H beams, okay? I mean the directions are X and Y. So probably I rotate it into the correct 90 degree to have the correct neutral axis. So I have an I beam similar like this, and you can also check from this when you launch the mechanicals, right? So you can also check its mass, its length, as well as its cross sections. The I here is referring to I Y, and I Z itself. It's similar with what the here is a little bit difference. 510 and 15.3. So we have 513 and 15.352. So that is the closest, but of course you can fine tune it to get the as close as possible in this case. Okay, so probably because of the radius of the fillets, okay, the curve itself. All right, it's okay. Then we can then do a meshing. So here again we want to be 2 nodes, okay, 1 element. So we put larger so-called size in this case. So we have so-called 2 nodes, right? Then we apply uh, here we apply the insert the supports as well as the loads. So load, we are putting a distributor load, so we have to select the line, okay, instead of the vertex or the node of the point itself. So the whole so-called the load itself is in Y component is negative 1,000 pound per feet, so it's equivalent to 83.333 pound per inch, right? Then we solve it, okay, and we look into the deflections or deformations in the y-axis only, the vertical, in this case is verticals. So we can find out that the directional, okay, is around, if you look into it, is at around, here is around 0.016, right? So, and also we can look into its rotations. Here is about the z-axis itself is also the slope. Then you can compare, okay? So you can find out that compared to our calculations, the original one, I mean, is 0.15 and 0.10016. So you can see that the deformations or the deflections in y-axis itself using its original beam models. Here we are talking about beam 188 models in NCs is slightly larger. Okay, so here is because of it is using different models, okay, as what we have calculated manually. So this is using a Timoshenko beam models. Compared to what we are using here is Euler-Bernoulli beam models. I mean, I've just now I didn't really mention it. So then this is the difference why we having calculations is 0.146, because our Euler-Bernoulli beam models, we didn't consider when it bends, you don't have this shear the deformations, okay, due to this shear force. But Timoshenko basically beam model basically consider these shear deformations when due to this shear force itself. So here beam 188 or Timoshenko beam model will have additional terms, the rotations, then give us a higher or larger deformations compared to Euler-Bernoulli what we call the beam models. Okay, so in the case of very long, okay, very long beams, so probably the effect of these two beam model will not have so much difference lah. When in the case of short, okay, when you talk about slenderness, a shorter length, so probably you will see a significant effect or significant difference between this beam 188 and what we call beam Timoshenko beam model and also the Euler-Bernoulli beam models. So what we did is we call as I mentioned to you is Euler-Bernoulli's. Okay, so ANSYS now is already using Timoshenko beam models. Okay, to solve it. Then of course you can still use Euler-Bernoulli where we call this beam 4. Beam 4 under ANSYS is under Euler-Bernoulli beam models. Okay, if I'm calling this out, then probably I have a very close results as my calculations. Okay, manual calculation. Our model is Euler-Bernoulli beam models. All right. So how to call it? Basically, it is not by default already. By default, probably it. I would say that it is using beam 188 already because it's more. It consider more another parameters in, okay, the shear part, rotation parts due to the shear force itself, where we didn't consider just now. It's more accurate. I mean, in the case of shorts, so-called short. Here talking about standard short beams, probably is more accurate. In this case, if you want to use beam 4 or Euler-Bernoulli, probably you have to use this what we call commands. All right, so you can add the commands here, okay, for your geometry. So I'm using Euler-Bernoulli's. So here you can have set the what we call the I, okay, the second moment of inertia. Then you have the areas, right? 10.3 is our area, right? Areas, then also our so-called I or second moment of inertia of areas, okay, both of them. Then probably, okay, then you can run it up, okay, then it will use these commands, okay, APDL commands to basically take the Euler-Bernoulli model or beam 4 model rather than beam 188 models. So Euler-Bernoulli beam theory will be a more simplified versions. I would say that compared to Timoshenko. So the only difference, if you look at what we are looking into, the formulations, we did not we consider the U, right, UI1, UI2, UJ1, UJ2 in one element, right? So we consider the vertical displacements as well as the rotations, and only happen to when if you look into actuals, this particular beam itself that you have seen here. So if this thing is bent, right? Okay, this thing is so-called bending like that, right? So you have its so-called bending moments m, as well as you have the shear force. Okay, so you have something to do with when you have subjected to a transverse loads, transverse loadings. Okay, so you will have shear force or shear force or shear loadings at that particular point. So these will actually generate a shear stress. So as well as the moment that generate your maximum normal stress lah. Right, so that actually combine. So when you are doing your MOM, so I'm subjected to a beam, subjected to a transverse load. So you have to look into shear as well as the normal, or shear from the shear force itself, right? So in what we have discussed, okay, under Euler-Bernoulli beam principle, so we assume that, okay, so the deformations, okay, subject to these transverse loadings, it is there is no what we call it shear. If you're looking into each section, this section itself, there is no shear deformation about its plane itself lah. So meaning to that, if you're looking into these two plane itself, right, so it won't doing a shearing effect. You don't have the shearing effects, okay, in between this. Okay, so that is under Euler-Bernoulli. Okay, so you won't consider this as shearing effects, but whereas you have under Timoshenko theory, beam theory, right? So that consider this particular effect coming in. Okay, so this particular effect itself will mainly affecting our stiffness. If you're talking about our stiffness matrix E elements, we have 4 times saw metric, right? So here is referring to UI1, UI2, UJ1, UJ2. So this particular effect itself, when you consider Timoshenko, then it will affect a lot on your rotation parts. Okay, so under Timoshenko beam theory, then it consider these shear deformations, okay, coming into play. Then it's more accurate compared to Euler-Bernoulli, where it's simplified. You don't consider this transverse loading shear deformations.